Okay, so we're going to keep talking about recognizing resonance patterns. And I'm going to give you a few examples of that. So one example that we talked about was allylic lone pair. And here we have, for instance, this functional group is an amide. This. And now notice that we have a lone pair on the nitrogen, and that is allylic to the double bond. Remember that. This here is an allylic position. And the ones here at the double bond, those are vinylic positions. So the electrons are allylic to double bond. So I can do this movement. That's one pattern I recognize. And I necessarily need to do another arrow not to break the octet rule. So now my resonance structure would be, I am creating a double bond here. And now this nitrogen has 4 bonds, no lone pairs, so it has a formal positive charge. And now oxygen will have 3 lone pairs, so a -1 formal charge. Overall, notice that this is a neutral species, and here we have positive and negative, so we have the same, say, net charge. So that's another allylic pattern. And I'm going to show you another example yet of a molecule. Now here, I'm drawing here. Let's do a double bond here and here. Bond, that. Now, what I want you to notice is, again, patterns. The electrons here are allylic to the double bond here. And these are, because of that, these are delocalized. So, meaning that we can do resonance with those. D is a delocalized lone pair. The ones on the top are actually localized. I'm going to use a different color. And so that's a localized lone pair. I cannot do resonance with those. It's not allylic to double bond. And on top of that, the carbon here is sp3, meaning that it has 2 bonds that are shown and 2 hydrogens. So octet is complete. I cannot move electrons over there. Also, this one is sp3 as well. So that, in summary, says that because these are localized, I won't move it. These are not involved in resonance. But the ones that are allylic to the double bond are. So I'm redrawing that structure over here to show you the resonance structure. So redrawing the same. Now we know these are localized, but the ones that are allylic here are delocalized. So I can do that. And notice I said that the carbon here is sp3, so I cannot move anything over there. The only thing I can do is now put the electrons at that carbon. So now the resonance structure would be the resulting after that electron movement. Now I'm going to have my nitrogen here. Now I don't have a lone pair, I have a double bond. And here I have electrons, a lone pair. And that is a resonance structure. Here, nitrogen with 4 bonds, no lone pair, has a formal positive charge. So we need to be able to recognize them when lone pairs are allylic like this, and when it's the case that we cannot move it. So we'll say those are localized. Reason being here that the carbon here, that's what? Is sp3, and that's also sp3. And I see that here. So I cannot move those electrons. So electrons in the bottom, on the other hand, are delocalized and are involved in resonance. We'll do more examples of these.